In this lesson, I'm going to provide a very brief conceptual overview of linear regression and its applications in epidemiology so that we can then move forward and talk about some applied analysis in SAS using linear regression concepts. If you have a really strong background in statistics, this introduction probably is not going to be terribly valuable to you, and you're well prepared to move on to the next lessons. The linear regression fundamentally tries to study the relationship between some response variable, usually characterized as y, and an explanatory variable, x. In epidemiological terms, we usually think of y as our outcome, or our dependent variable, and x is the explanatory variable, or oftentimes an exposure or a treatment. Generally, with linear regression, y should be some sort of continuous variable. Blood pressure, age, height, weight, variables of that nature are commonly used as outcomes in linear regression models. And x is often also continuous, but it may be categorical. The categories could be ordinal, meaning that the different levels of the categorical variable have some sort of inherent order to them. And you can even model nominal categorical variables as independent variables in a linear regression. Generally, you need to use some special techniques to make appropriate inference, and we'll talk about those techniques in subsequent lessons. But the form of the x variable in linear regression can be varied, whereas the form of the y variable, or your outcome variable, generally needs to be a continuous and normally distributed variable. As we said, x can have many different values. Usually there'll be at least some variation in your x variable, of course. It's possible to model an x variable that has as few as two different values. Take a variable such as gender, or maybe comorbidity status. Do you have diabetes or not, as a predictor variable? That would take on two levels, and it's possible to model that type of explanatory variable in linear regression. It's also possible, and quite common, to use x variables that have many, many different values. You could take age for an example. Imagine you have a cohort of individuals who are 20 to 40 years old, and each individual in the cohort in your data set has a value of age rounded to the nearest whole number. So you have 20-year-olds and 21-year-olds and 22-year-olds, etc. In that context, you can start to think about each x value as some subpopulation. And then you assume that each value of x is going to correspond to some underlying mean value of y in the population. So if we think about something like age and blood pressure, we're thinking about the many different means of blood pressure as they vary across groups of individuals according to age. And then with linear regression, we're really starting to try and focus on the many different means of y and how they change according to changes in x. Now, this is the linear regression equation, and even if you have absolutely no background with linear regression, it should be somewhat familiar, as it's simply a straight line equation. And in this straight line equation, we are modeling the mean value of your outcome variable, which is set equal to an intercept term, beta naught, plus a slope, beta 1, that will tell us to what degree the y variable changes according to x. So this is the coefficient that is multiplied with your explanatory variable to try and give us some sense of how y varies with x. And these are simply describing the terms in a bit more detail. Again, in the context of linear regression, the beta 1 coefficient is usually what's of most importance to us. This is the slope of a straight line, and as I said, it's telling us how y changes according to changes in x. Here's an example of a straight line and the equation that fits that straight line. This particular example is a bit idealistic, but it's regressing blood pressure on the y-axis across age on the x-axis. And you can think of each point as a mean value of blood pressure according to individuals of different age. So here are the 20-year-olds and the 21-year-olds, etc. And in this particular example, a straight line fits the data perfectly. In other words, if we know somebody's age in this particular sample, we can perfectly predict what the blood pressure will be, because the straight line goes through the points perfectly. And you see here we have the equation, 0.5x plus 105. So the literal interpretation of this is that when x equals 0, systolic blood pressure in this example would be equal to 105, or the mean systolic blood pressure. This intercept with 105 has no meaning in this particular context because you can't have an age of 0. So the real coefficient of interest is beta 1, which is equal to 0.5, and that's telling us for every 1 year increase in age, there's a half millimeter mercury increase in systolic blood pressure in this hypothetical data set. And the R square simply tells us that age explains 100% of the variation in systolic blood pressure. Well, this is a bit idealistic relative to real-world epidemiological settings where the data are never quite so clear. So here's another example where you see that there's a general pattern. If you look at these individual plotted points of systolic blood pressures as they vary across age, there's a general pattern of increasing age being related to increasing blood pressure, but it's not a perfect relationship, and it would be impossible to draw one straight line through these data that would capture all points. So one of the notions in ordinary least squares of regression is to try and figure out the best line to go through that data, the line that best represents the data, and then you can generate your straight line equation, and from that equation you now have information about a relationship between your explanatory and your outcome variable. The question is how to calculate that straight line. What do we mean by the best straight line? And in the context of least squares regression, we're talking about the line of y on x that minimizes the sum of squared deviations between your regression line and the actual observed values. Or in other words, we want to reduce our cumulative residuals in the data. And the residual, again, to give a visual example, is simply the difference between the observed points. So in this example, here's an observed systolic blood pressure of about 119, and the predicted value. And here the predicted value is a little bit more than 130. So you would have a residual of about 10 or 11 in this particular example, and you could go through and calculate residuals for every point along this line and sum those up. And then you could redraw another line and once again go through and sum up all the residuals, and you do that over and over, and you try and converge on a regression line that minimizes the variability or the residuals between observed and predicted values. And that's how you come to the best line, generally speaking, in ordinary least squares regression. So just to give a visual of that, you have your data plotted out here in a scatter plot, and you might start with a horizontal line, which does very well with 3 or 4 data points, but for the vast majority of data points, it's way off the mark, and you're going to have a lot of residuals. So you may calculate another line that you think would work, and then another line, and you keep going until finally you converge on the line that best fits the data. And again, in terms of best data fit, we're talking about the line that comes as close as possible to all of the data points, and that's measured numerically by reducing the sum of residuals between the observed and the predicted line. Once you have your regression line determined, there are a number of ways that it can be used in public health and in epidemiology. So first of all, you could calculate predicted mean values of the dependent variable given certain values of an independent variable. And prediction models are quite commonly used, and linear regression contributes to that type of prediction quite often. Another example, certainly in etiological epidemiology, you can interpret the regression coefficient, particularly beta 1, and in doing so, this allows us to make inference about how a dependent variable changes according to change in an independent variable. So this is quite commonly used and very useful within the context of etiologic epidemiology. It's usually very difficult to make strong causal inference based on a simple linear regression model, but if you have the right epidemiological design combined with a linear regression model, you can make some causal inference. For example, if you have age as your predictor and you're looking at change in blood pressure over the next 5 years in a cohort study, you may have better ability to make some causal inference about the role that age may have played in subsequent blood pressures, holding all other factors constant, of course. In summary, linear regression is a very useful and commonly used tool in epidemiology. A core assumption is that X and Y have some sort of linear relationship. If you think back to the graphs we saw, if they don't have some component of a linear relationship, the line simply is not going to tell the full story, and there are other models that would be appropriate. But nevertheless, if there's at least some component of the relationship that is linear, you can gain a lot of information about how dependent variables vary in relationship to some explanatory variable. Linear regression is appropriate for many different kinds of continuous variables that we discussed previously, ages and cholesterol levels and heights and weights and blood pressures, caloric intake, etc. However, be careful, for those of you that are not as familiar with linear regression concepts, linear regression is not appropriate for categorical outcomes. There are other methods that will handle a categorical outcome better, and you should seek those methods if that's what you're dealing with, and if you're trying to predict something that's more categorical in nature. So a really common example of a categorical outcome would be heart attack, yes or no. Incident diabetes, yes or no. If you're trying to construct models to predict those kinds of binary outcomes, there are better methods for handling those types of outcomes, and linear regression would not be appropriate.